So it's my great pleasure to introduce our speaker today, Nathalie de Leon from Princeton University. And so I'll give you a little bit of background about Nathalie. So she did her bachelor's in chemistry at Stanford and did a PhD in chemical physics at Harvard with Hong-Koong Park. And then did a postdoc at Harvard jointly with Misha Lukin and Hong-Koong. And that's, I think, when I met Nathalie. I actually don't remember if we met first while you were still doing your PhD or during your postdoc, but I had the pleasure of overlapping with her and getting a chance to see her in action before she started her faculty position at Princeton. Nathalie has sort of, well, first of all, she's done really important pivotal work in a bunch of different fields and related fields, including nanophotonics and plasmonics, quantum optics, diamond fabrication and materials characterization, and also lately has really been leading the charge on characterizing and understanding new defects in diamond, and also in sort of understanding fundamental sources of decoherence and noise in diamond and other solids, which I think we'll hear about today in her talk. She's been awarded too many early career awards to count, DOE early career, NSF career, DARPO young faculty, AFOSR young investigator, so pretty much every letter in the alphabet, I think. What I find most impressive about Nathalie's research, and I think this will be, you'll see this quite apparently in her talk, is that we talk a lot about these days about how quantum science is becoming interdisciplinary, but for most people that's sort of just a buzzword, or it means you have to kind of collaborate with people in a bunch of other fields. But Nathalie is truly interdisciplinary and does really interdisciplinary work. She's a PhD in chemistry, who's a professor in electrical engineering, who publishes most of her papers in physics journals and is giving an AMO seminar. And not only can she kind of fit in with any of those fields, but she could give sort of highlight talks at conferences in any of those fields, and I think does regularly. And so anyway, it's my pleasure to turn it over to Nathalie.
Well, thank you for the really kind introduction, Shimon, and thanks so much for the invitation to come talk. This is, as Shimon mentioned, my group, is sort of fortunate enough to be a member of many different communities, but don't tell anyone you guys are my favorite community. So I do love giving atomic physics seminars because I think I get really great questions at these colloquia. So today I'll be talking about a couple of different projects in my group that are focused on trying to do sort of systematic improvements to quantum systems by trying to correlate materials analysis with qubit measurements. So just to kind of set the stage, the basic perspective in my group is that what we usually like looking at are atom-like systems in the solid state. So there's now been several decades of work developing atoms, particularly cold atoms, as these really beautiful quantum systems. Of course, they can have very long spin coherence times that are this kind of nice playground for storing and manipulating quantum information. But very importantly, they also have very efficient optical transitions that you can use to try to manipulate and read out these quantum degrees of freedom. So what we're interested in doing is looking for systems that have these essential properties but exist in the solid state, so that you can imagine integrating them into kind of these scalable, solid state devices. And this has a lot of different applications in quantum information processing, but also quantum networks where you can now couple to a photon and send that photon over very long distances. And then there's a unique kind of opportunity for a completely new application space if you find a solid state quantum system, which takes advantage of the fact that you're really localized to these extremely tiny length scales, and you have these things that act as true point sensors. So we're sort of interested in trying to develop these nanoscale sensors. So the efforts in my group these days are sort of divided into three. So we're working a lot on nanoscale sensing and surface spectroscopy based on color centers in diamond, specifically the nitrogen vacancy center in diamond. As Shimon mentioned, a large effort in my group is also aimed at trying to find new solid state defects and develop integrated nanophotonics for quantum networks. And then very recently, within the last year or so, we've also started, I guess, a year and a half, the whole last year is just one big blur, so it's hard to keep track of time. So for the last year and a half or so, we've started a completely new effort in my group looking for new material systems for quantum computing, and specifically taking a hard look at what kind of material systems you can deploy in superconducting qubits. So I don't have time to talk about all three things today. So I'll just mention that we work on quantum networks, and I think there's other recorded seminars on the internet that you can look at that are related to that. But today I'll be talking about sort of these two projects in my group. So the nitrogen vacancy center in diamond is a point defect that consists of a substitutional nitrogen next to a vacancy in the diamond lattice. And it turns out that this defect gives you extremely deep electronic levels inside the diamond band gap. So if you look at the valence band and conduction band extrema in diamond, the ground state for NV is something like halfway between these two band edges. And then you have enough headroom, given the very wide band gap of diamond, that you even have room for excited orbital states that are very, very far away from these band edges. So to first order, you can really think of this as a trapped molecule where you just think of linear combinations of atomic orbitals giving you molecular orbitals, and you don't have to consider kind of the continuum of states from the band structure of diamond. The NV center in particular is an electronic spin 1 defect that has extremely long coherence times even at room temperature. So you have a spin lattice relaxation of around 10 milliseconds. And your T2 is generally just sort of limited by what kind of nuclear spin bath you have. And it turns out that there's a really convenient way to optically manipulate and measure the spin. So even at room temperature, there's a scheme for doing off-resonant excitation and spin readout. Basically, if I just shine, a laser that is about as sophisticated as a green laser pointer at the NV, and I just look at how many photons I get back, then if I start in ms equals 0, I can cycle a bunch of photons and get some high fluorescence rate. But if I start in one of the other two spin sublevels, I have a rapid intersystem crossing to a dark state, and then that suppresses my fluorescence a little bit. So this is optically detected magnetic resonance. And I can see, this magnetic resonance just by measuring fluorescence. And you can use this, for example, to measure the local magnetic field, because you can see Zeeman splitting between these different sublevels. People have shown that you can coherently manipulate and measure the spin. And basically this set of special characteristics, that you have this long spin coherence time at room temperature and this optical readout, has really spurred work among dozens of groups around the world looking at this one color center in diamond. One of the things that people are particularly excited about is that you can use these things as nanoscale sensors. So you have these long spin coherence times at room temperature and this really convenient method of readout and initialization. And then if you take kind of, the many, many decades of work that people have done in figuring out how to do magnetic resonance and apply, sophisticated pulse sequences to figure out what's going on, and you combine that with the work that people did over the last 3 decades or so in figuring out how to do single center imaging, then the really exciting prospect here is you have this point sensor that you can read out, and you can use that to look at the local environment. So people have used this to try to look at ensembles, within a very small volume right on the diamond surface. And there's an enormous amount of work using this for things like condensed matter sensing, where you can map, magnetic fields and magnetic textures in some nearby material system. Sort of pushing this to, really incredible single atom scales, people have also started now looking at doing something that looks a lot like magnetic resonance imaging, but at the single atom or single molecule level. So the idea is that you can think of this NV center as having, sort of the largest possible magnetic field gradient for MRI, because you really have this point sensor, and then that enables you to get extremely high resolution. So this is a beautiful example out of Tim Tamignau's group from a couple years ago, where they took an NV center and then used it to resolve the positions of individual carbon-13 nuclei in the diamond lattice. So the promise of this technique is you can now imagine really doing, MRI at the single atom level, looking at, for example, the thing that we always write in our grants, our grant proposals is, you take a protein, stick it on the surface, and then try to do protein structural determination in real time. And in principle, deep in the diamond in very high purity environments, this already works quite well. So, okay, so what are the challenges? Why is it that we have not, just deployed this for wide scale biophysics experiments already? So in order to take advantage of both, this high sensitivity sensor and to get really high resolution, you need to get very close to the target that you're interested in. But if you get close to this sensing target and you're trying to look at anything that's not just inside the diamond, you also end up having to be very close to the surface. And while we're very good, as mankind in making extremely high purity bulk diamond, we're generally quite bad at making good surfaces. It turns out we're actually really bad at making most surfaces, but diamond surfaces are even harder than, other surfaces. So what happens is if you see, this background spin bath, then that obscures the signal that you would like to see coming from your sensing target. And one of the ways that we know this is if you just look at individual NV centers and map out their coherence time as a function of depth away from the surface, we see this really terrible scaling. So again, deep in the bulk of diamond, your T1 at room temperature is something like 10 milliseconds. And when you get within tens of nanometers of the surface, you start to see something that looks a lot like power law scaling. And by the time you're within a few nanometers of the surface, you see more like hundreds of nanoseconds of coherence. And this is, all of these data points are from my group that are, the different colors are different samples that are prepared in slightly different ways, but you can see that they all kind of fall along the same scaling, and many other groups have observed really similar things. So what we set out to do about 4 or 5 years ago was figure out how to understand this surface noise and try to use, microscopic understanding to mitigate these problems. And the challenge here is that the NV center is a very sensitive probe and it looks at its local environment, but it's very non-selective in that, all that it can kind of tell you is I'm seeing a noisy environment, and maybe you can do a little bit better and look at the spectrum of the noise, but it doesn't really tell you anything about the microscopic nature of the noise that you're looking at. So we sort of set out to look for surface sensitive techniques to just directly look at the material. And these surface sensitive techniques, are generally challenging for a variety of reasons. Mostly you're looking at this monolayer of atoms on top of this bulk. So you have to come up with a bunch of tricks to be mostly sensitive to that monolayer of atoms. But okay, there's a whole field of people who have been working on that for quite some time. But maybe more fundamentally, these techniques generally probe much, much larger areas than what the NV center is looking at. So a priori, it's not obvious that you're going to find information that's relevant to the local environment of the NV center. And in addition to that, there's a large number of technical problems with respect to looking at diamonds specifically. So what we set out to do was to try to develop techniques to study the diamond surface in detail by correlating a lot of these traditional spectroscopy techniques with nanoscale spectroscopy that you could do from the point of view of the NV center. So we kind of did a little bit of a scattershot approach at the first instance where we just tried really any synchrotron beam time that we could get our hands on and any bit of materials analysis in-house. So everything that's grayed out here is stuff that we tried that didn't give us particularly useful information. But we ended up landing on a bunch of photoelectron spectroscopy tools. So this is X-ray photoelectron spectroscopy, ultraviolet photoelectron spectroscopy, and near-edge X-ray absorption fine structure spectroscopy. All of these techniques basically give you some probe of either the density of states or the density of unoccupied states, and you get your surface sensitivity by relying on the very short inelastic mean free path of electrons coming out of the material. And the reason that we zeroed in on these techniques is that we could then correlate, information that we saw with something a little bit more sophisticated than just asking the NV center if it had a long coherence time. You can do some nanoscale spectroscopy to figure out what's going on in the local environment of the NV. So I'll cut a fairly long story a little bit short and just give you the highlight reel of things that we discovered about the diamond surface. So one of the things that we saw sort of immediately is that a lot of people in the community were using, oxygen terminated surfaces, and then they would just say, we oxygen terminated the diamond. But what we found was that sort of depending exactly on the method of oxygen termination you use, and specifically depending on the surface morphology, you can have enormous differences in the characteristics of the surface. And the real problem here is that processing in diamond tends to be very hysteretic. So if you do some oxygen processing, what happens is you have an enormous etch rate anisotropy of different crystal facets in your diamond. So that means that if you start with, say, two substrates that have just very slightly different surface roughness, and then you put them through the exact same process, you can end up with, this surface stayed pretty smooth, and this surface has this kind of crazy surface roughness at the end. And we could see direct consequences to the electronic structure of this kind of surface morphology. So if we now take this rough surface and the smooth surface and put them in this NEXAFS spectroscopy, we can see that the rough surface has this enormous density of unoccupied trap states that are sort of near the conduction band edge. So what you're looking at here is everything. This is the exciton peak in diamond. Everything to the right is sort of the band structure of diamond. Everything to the left really just shouldn't be there. So these are basically, trap states that can serve as sources of magnetic and electric field noise. So using this kind of feedback tool where, we identify that one of the critical pieces is that you really need to maintain this smooth surface morphology while maintaining, well-controlled surface chemistry, we came up with sort of a laborious process for creating pristine oxygen terminated surfaces. We start with, state-of-the-art polishing that gives you low subsurface damage, and then these sort of very shallow polishing grooves and sub-nanometer surface roughness. But then that leaves behind a large amount of subsurface damage that gives you very highly strained layers. So you need to remove that by reactive ion etching. That RIE leaves behind some implanted ions that are a big problem for NV stability. So then we have to do more RIE to get rid of that etch damage. And then we have to do thermal annealing to get rid of that remaining etch damage. And finally, some chemical treatments to get rid of the disorder that we induce during the thermal annealing. So this is a little bit like, you start with a mouse problem and you release the cats, and now you have a cat problem, so you release the dogs, and hopefully at the end of this chain, you have gorillas that die in the winter. So now we're basically left with these very pristine oxygen terminated surfaces that have a very smooth surface morphology and very low contamination. So just to give you the headline result, after doing all of this processing, what we're able to do is improve the coherence time of shallow NV centers. This is these dark green points here by a little bit, by basically an order of magnitude at the same depth. Okay, so now if you don't want to hear about surface spectroscopy, you can just kind of fall asleep for the next 10, 15 minutes, but I'll basically just go through, the different pieces of evidence that we have for these different surfaces. Okay, so to understand, how we were able to see this improvement and what the microscopic underpinnings were, what we did was we zeroed in on kind of these two last surfaces. So this isn't the most heavily damaged surface, but we wanted to see what change you got from this final oxygen annealing step. So from the point of view of the NV center, we can, look at the coherence time, and this is on a log scale, and we can see that after we do this last oxygen annealing step, we get an improvement of, a little more than a factor of 2. And then importantly, if we do dynamical decoupling to probe what the noise looks like over higher frequencies, before you do this oxygen annealing, we see that as you increase the number of pulses, the T2 actually saturates. So you have this very broadband noise bath that you could not really just dynamically decouple your way out of. And then after you do this oxygen annealing, we see this kind of nice scaling with T2 where we're able to enhance the coherence time over a very large range. We can also take advantage of the fact that the NV center has a spin 1 ground state and do relaxation spectroscopy to try to disentangle, whether we're mostly looking at magnetic or electric field noise. So the general idea is that magnetic noise can drive these single quantum transitions that change your angular momentum by 1, but it generally will not drive transitions between your ms equals plus and minus 1 sublevels, whereas electric field noise can actually couple these things. So what we see is that if we look at our single quantum T1, we get this very large difference as we do this last oxygen annealing step. Whereas if we look at the double quantum T1, it's a much smaller difference. So this indicates that the change in noise that we see is predominantly magnetic. If we sort of put all of these pieces together, because I had a little bit of a sleight of hand, all of these different techniques are actually probing very different frequency ranges, and you have to sort of take into account things like 1/f scaling. Then what we see is that this is sort of what you expect from electric field noise, whereas this is sort of a picture of what your magnetic field noise distribution looks like. And you can see that we have this very broadband noise source that is, predominantly magnetic. Okay, so that's what we can learn from the point of view of the NV center. So now we can turn to this direct surface spectroscopy to see, what differences we can see between these surfaces. So sort of to my surprise, if you just look at this NEXAFS spectrum, where again, what we're doing is probing the unoccupied density of states. If we go and zero in on the oxygen edge to look at kind of the chemical nature of the surface termination, okay, maybe a surface spectroscopist would be really offended at this characterization, but I would say that these look very broadly similar. So I have, a sharp peak here and some broad shoulder. So I think the story is not as simple as we're just changing between, you have a ketone termination and you're turning it into an alcohol or something like that. But instead, what we can see is that if you, for example, change the polarization of the incident X-rays by tilting your sample, in this acid clean surface, we see very little polarization dependence. Oh, sorry. Whereas in the oxygen annealed sample, we see this really dramatic polarization dependence. So what this really points to is that these surfaces are somewhat chemically similar, but the acid clean surface is highly disordered, whereas the oxygen annealed surface has these atomically ordered bonds because that allows you to see this polarization contrast. We also saw that, also sort of to my surprise, that if you did ultraviolet photoelectron spectroscopy, which is sort of a probe of the work function and the electron affinity, that we saw this enormous difference in the electron affinity, by over an EV between these two surfaces. So even though the oxygen coverage was kind of similar, you basically, completely move this conduction band edge by about an EV. And actually in doing this work, we solved kind of a long-standing puzzle in the field, which was that if you just did calculations of what the electron affinity should be for hydrogen terminated diamond, if you made it and compared it to calculations, you were basically spot on. But for oxygen terminated diamond, people generally saw this discrepancy of 1 to 2 EV. So, what we sort of showed is that the degree of disorder in the surface gives you a large number of electronic traps that really change your electronic structure enough to move your electron affinity around. Okay, so that's putting everything together. And then just to show you that, we're actually able to really gain a lot of control over these surfaces by being very careful about our processing. What we were able to show is that the surface termination is very reproducible and reversible. So if we look at a single NV center at 7 nanometers with this coherence time, we can do this final oxygen annealing step to enhance the coherence time. We can reset it by thermally annealing, and then we can do a final oxygen annealing to kind of bring the coherence time back. And what we find is that this is pretty reproducible across every NV center that we look at. Okay, so just to briefly kind of summarize just this very first part of the talk, we were able to use complementary spectroscopy techniques to discover sources of noise. And that enabled us to create a diamond surface with very highly ordered termination that's very smooth, and that allows for NV centers that are within a few nanometers of the surface with 100 microsecond coherence times. And okay, so I think I was supposed to leave in a couple of natural stopping points for questions. So I'm going to say that this is a natural stopping point.
Yeah, great. We have a number of questions. I don't think we'll be able to get to all of them, but we can ask a few of them. So so first question, as is traditional, comes from Bill Phillips. So why is it harder to make good diamond surfaces? What surfaces are easy and why?
Yeah, so the main two problems with diamond, sorry, I'm going to say that there are three problems with diamond. So one is that it's very inert. So a lot of chemistry that you would like to do, like wet chemistry, doesn't really work on diamond. So to give you a contrast, for something like silicon, it's relatively easy to control the termination because there exist methods where you can oxidize the surface and then remove it. And there is no such chemistry for diamond. Part of the reason that no such chemistry exists is that in addition to being inert, number two is that it has a very, very small lattice constant. So just because you have this extremely sterically hindered environment, it's both hard to attack it with chemicals and it's very hard to fit any groups on it. So you just don't have access to that many types of termination. And then the third issue is very prosaic. It's just that it's extremely hard to polish. It's the hardest material in the world, and polishing diamond is more like this horrible war of attrition where you kind of bang diamond against a wheel that is impregnated with more diamond. So it's a whole art in and of itself, just getting smooth surfaces to begin with.
Great. So then there's a question from Christy, and I think Norm actually added to it as well, which is Christy asks, are there other viable or competitive options beside oxygen termination? And then Norm added to that sort of, and is there some chemical intuition for why oxygen termination is actually, good or works well?
Yeah, so I would say that this space hasn't been explored very thoroughly yet, at least experimentally. So I would point you to, Adam Gali has a lot of work on calculating the properties of different diamond surfaces to try to come up with new things that might be worth exploring. But the two that are kind of easiest to make are oxygen and hydrogen. So oxygen you sort of get for free, because if you just acid boil the diamond, which is what you sort of have to do to just clean it before you get started, then you get this horrible mixture of oxygen states. So what we were doing was just trying to take that mixture and turn it into something that was much more well-ordered. Hydrogen you also sort of get for free in that diamonds are grown in a hydrogen-based plasma by CVD. And they come out hydrogen terminated, which also means that you can just sort of put them back in plasma and re-hydrogen terminate them. Hydrogen termination is actually better in the sense that you get a less defective surface, but there's a technical problem that you get a negative electron affinity surface that gives you this charge transfer to surface adsorbates, and then that gives you band bending that destabilizes the NV charge state. So actually there is an effort in my group trying to look at NV centers under hydrogen terminated diamond in UHV conditions where you don't have this charge transfer process, where the hope is that actually we do expect that to be a better surface from the perspective of defect density.
Okay, let's see. So maybe we'll do one more question and then we can move on. So Chong Zhu asks, after the oxygen termination, does this termination degrade with time when it's, for example, exposed to air?
So we don't entirely know. And sorry, I have to think carefully about what data we actually have that we know for sure versus what we believe superstitiously. So one of the complications is that everything gets sort of dirty over time. So what we know is that we'll see degradation in NV center properties if we're looking at it long enough. But what we have not done is disentangled how much of that is stuff accumulating on the surface and causing problems versus the actual surface termination changing over time. So I'd say we definitely have evidence for stuff accumulating. that part is clear. What we don't know is, what the causality actually is for the degradation.
Okay, great. I think we can move on and we'll save some of the rest of the questions for later.
Okay. All right, so everything that I've told you about so far in terms of NV characterization is fairly conventional, right? We're basically just doing dynamical decoupling to try to probe the frequency of the noise. So what I wanted to tell you about was a more recent story where we were able to do a slightly more detailed characterization of the bath that of the noise bath that the NV centers are looking at. So this is a second story about trying to do nanoscale spectroscopy of spins that reside at the surface of diamond. Okay, so our main tool here is doing double electron resonance measurements where you do a Hahn echo on your NV center, and then you apply a selective pi pulse to another bath of dark spins that you can't address optically. And basically what you see is that if you just apply this Hahn echo, you get this decay. But then if you put in this pi pulse that selectively addresses this other bath, you get this decay. And now if I just divide out these two curves, what I get is something that gives me basically the free induction decay of these surface spins. Okay, and we can do this to read out sort of what the coupling strength is to these surface spins. And what we find is that, in general, you get this coupling strength. It decreases with depth with some scaling, which really tells you that these things kind of exist at the surface. And we can prepare different kinds of surfaces that have different densities of these surface spins, where we have higher coupling for all of these points. And then here we have, lower coupling rates on average if we try to suppress this density. Okay, so now what we'd like to do is, go into the X-ray spectroscopy and the surface spectroscopy to figure out whether or not we see any feature that correlates with this deer signal to see if we can figure out what gives rise to these surface spins. And what we find is that if we look at the carbon K edge in NEXAFS and we zoom in on this little region here, there's this little tiny peak that shows up around 282.5 eV. That's in samples where we have a lot of deer contrast or a high deer signal, and then it's gone in samples where we see lower deer signal. Okay, but I just showed you a giant pile of data saying that a lot of things change when we do this last processing step. So that doesn't tell me that I necessarily have found the culprit for my deer spins. So we had to set out to find a more selective annealing procedure to get rid of this dangling bond peak. So in situ in the synchrotron beamline, what we can do is some annealing where we see that this oxygen edge really doesn't change very much if we anneal at around 650 degrees. But now if we zoom in on this dangling bond peak, you see that that disappears at 650 degrees. So we know that this dangling bond kind of goes away. And then similarly, now this is a much larger data set where we are looking at a bunch of NV centers in one sample, and now looking at the exact same NV centers before and after plotting this deer signal, you can see that it gets suppressed by around a factor of 3 or 4 after we do this annealing. Okay, so this is nice. It looks like we have some dangling bonds that are responsible for these surface spins, but we immediately kind of saw one big puzzle in the data. So the first puzzle is that this scaling of deer coupling with depth corresponds to a density of surface spins that is 0.005 per nanometer squared, which is a linear spacing of around 14 nanometers between surface spins. So that means that we're operating in a regime where the NV is much closer to these surface spins than the surface spins are to each other. So in that regime, you would not expect to see this kind of nice monotonic scaling, but you should instead see some increased variance as you go closer to the surface, because you should accidentally be really close to some surface spins and occasionally very far away from some surface spins. Okay, so that's the first big puzzle. The second puzzle is that if we tried to fit our free induction decay signal, so this normalized deer signal, very carefully, what we found was that it did not fit well sort of to the form that we expected. So in general, you can just write down that if you have a quasi-static bath, this free induction decay signal should look like e to the minus gamma tau to the n, where this n is exactly 2. But you can see that if we try to fit this to an n of 2, this is kind of the best fit, and that provides a really poor fit to the data. And actually, this whole project, there's a little bit of a funny story here that basically I had this very talented intern student in my group, Yahya Nasab, and he was very dutifully taking all of this deer data, and then he'd give me back these fits that were that just didn't make sense, like they had these extremely low exponents, and I just assumed that he was wrong, and I just made him go back and fit the data, because you never believe the intern, right? But then COVID happened, and we were all stuck at home, and we had nothing better to do than to really carefully fit our old data. And I realized that actually this entire time he was totally right, and we should have been paying attention to these exponents. So what we did, we put a data set together with our friends in Misha Lukin's group, so Bo Dwyer, Ilana Urbach, and Ilana Urbach had this fairly large data set as well. And we started carefully fitting all of the data. And what we found was that actually n equals 2 is a really poor fit to almost all of the data that we were looking at. And in general, you see this sort of depth dependence to your exponent. And also, much to our surprise, we saw a large number of exponents that were below 1. And you can sort of write down a pretty simple argument that you should have a strict bound on this n between 1 and 2, as long as you have well-behaved and monotonically decreasing noise. Okay, so that's puzzle number 2, that we see these stretched exponents for our coherence decay. And then the final puzzle that maybe gives you some sense of what might resolve all of these puzzles is that we found that coherent coupling was extremely rare. So I already told you that these NV centers on average are actually much closer to the surface spins than they are to each other. So you would expect to see coherent coupling in almost all of your NV centers. But instead, we would see this in something like a couple percent of all of the NV centers we looked at. And then occasionally you could even see that this coherently coupled signal would sort of blink on and off on human timescales. Okay, so those are our 3 kind of puzzles that you don't see statistical variation, you never see coherent coupling, and then we also have this weird stretched exponent. So one guess at what might give you the stretched exponential decay is, for example, if you imagine that you have an NV center that's talking to a really high density bath, and that gives you this nice n equals 2 coherence decay. But then at other times, it's talking to a low density bath, which also gives you an n equals 2 coherence decay. But if the NV center sees both of these things and averages over these 2 configurations, then what you end up with is something that has an n that's less than 1. So it appears to be a stretched exponential. So basically, one question is it possible that the NV center is looking at some configurational averaging of the surface spin bath? And then separately in my group, we were working a lot on photoionization dynamics of NV centers in diamond, where you know that if you just shine green light on the NV long enough, then you can get this 2-photon ionization into the conduction band, and then it switches charge state to NV0. And we knew that we could monkey around with this photoionization quite a bit. So it's sort of a natural question. Well, is it possible that these surface spins are also getting photoionized, and then that scrambles their positions? Okay, so we can now just do numerical modeling of what happens if you're sampling these different geometric configurations at the surface where they're in 2 dimensions. And what we find is that just from numerical modeling, if you look at NV centers that are at very deep depths where they see a large number of different surface spins, then you indeed do recover this n equals 2. And then as you approach the surface, then what you actually see is that the NV center looks like it's part of a 2D bath of spins. And it turns out that the exponent should look like d over alpha, where d is the dimensionality and alpha is the strength of the interaction. So you end up with an n of 2/3. And then as you increase the density of the surface spins, then of course you change the depth at which you see this transition happen. So this likely accounts, for this kind of funny exponent that we see. So then we can write down sort of an analytical model for what these exponents actually should be. And it's not that easy to solve analytically, but we can solve it in a couple of limits. So at very, very short times, we sort of recover this e to the minus gamma tau squared. And then at very long times, then we get this exponent of 2/3. And actually what we find is that instead of getting, some random exponent that's in between, what we see is that as a function of time, you see a critical crossover between this n equals 2 and n equals 2/3 limit. So this is a simulation plotted on a log plot, which is not that easy to think about, but it gives you the nice visual cue that the slope of this curve is just the exponent of this coherence decay. So you can see that you go from n equals 2 to n equals 2/3. And then now the time at which this crossover happens just depends on the depth of the NV center. So sort of a very nice geometrical interpretation of this, that at very short times, the NV center sees many kind of contributions from a lot of distance spins. And then at some critical time, that's set by the depth of the NV center where it starts to see the surface, then it's coherently coupled, it's strongly coupled to a few spins. And then it starts to see this configurational averaging so that it starts to see this 2D bath. And you get this exponent of 2/3. So I have this video that hopefully plays nicely in Zoom. But basically, if you think of this as being the sphere that encapsulates how many spins the NV center can see in strong coupling, then there's some time delay before it hits the surface, and then you start seeing this area law scaling. Okay, so now armed with this understanding of the data, we can go back and and measure the NV centers in a way where we really oversample this coherence decay so that we can look for this critical crossover time. And indeed, we do see that there's this dramatic change in slope. And remarkably, this crossover time really does just look like the distance from the surface, which we can measure independently using proton NMR. So everything that I've told you about is actually, sort of a generic feature of disordered spin ensembles, and you should be able to see this in principle in things like ensemble NMR and ensemble ESR. But the key kind of difference here is that this crossover time is going to be set by sort of the closest distance between spins that's possible. So in a normal solid, because that's going to be at lattice constant scaling, then it's very hard to actually see this time scale. So here, because the NV center is a separable probe, we can set this distance arbitrarily, and that allows us to set this time scale arbitrarily. So it's really something that's a feature of this nanoscale sensor that's different from the stuff that we're probing, that we're able to see this physics. Okay, so just as a very quick summary, what we've shown is that the NV center provides this really nice local probe of external spin systems through very careful measurements of decoherence. And specifically that, just carefully fitting this exponent gives you this nice probe of the dimensionality of the bath that you're looking at and the dynamics. In this system in particular, we find that the surface spins are hopping around, which has a lot of implications for how you might use these things as sensors. And then I'll just emphasize that here, the ability to separate the NV center, your sensor, from the system that you're studying is really key. So this also has implications for the various experiments around the world that use scanning probes with NV centers in them. So I don't have time to talk about the other kind of NV activities in my group, but I mentioned very briefly that we have some work looking at the charge dynamics of shallow NV centers. I'll also mention a couple of the chemistry efforts just very briefly. So one of the things that we've been working on intensively over the last couple of years is trying to interrogate NV centers in ultra high vacuum conditions. So as I sort of alluded to in the brief first Q&A section, you're very sensitive to surface contaminants. And so far, nobody has really looked at a contamination-free surface because you actually need ultra high vacuum conditions to do that. So what we have is sort of this surface preparation and chemistry chamber where we can really prepare these pristine surfaces. and then an attached UHV cryogenic confocal microscope where we can look at NV centers without breaking vacuum. And then finally, we're also starting to take a stab at another part of this problem, where if you want to now use this NV center to look at some molecule, fixing the NV center is only half of your problem. You also need to get this molecule somehow on the surface and next to your NV center in a biologically relevant condition. So what we've been working on together with Robert Knowles's group down in chemistry is trying to apply, modern catalysis techniques to the diamond surface to see whether or not you can actually, do wet chemical synthesis on the diamond to expand the scope of things that you can attach to the surface. And this has been a really exciting collaboration to get started. Okay, so I think that's another kind of natural stopping point before I start talking about superconducting qubits.
Great, yeah, so I think we can stick to just a couple of questions about the last section. So Chong Zhu asked, for the stretched exponential, when you first showed the data, it sort of looked like the coherence might not decay to zero. Was that just an artifact of it being stretched? Yeah, there you go. Does it?
I think we might just not have waited long enough in this data set. I'm hesitant to make any strong claims just based on what's on this slide.
Sure. And then, so Norm asks, does one have a sense for the length scale associated with how far the surface spins can actually move when they're photoionized? And then I had a related question of, did you look for, or can you see the sort of optical power dependence of the photoionization of the surface spins?
Yeah, so those are both really good questions. So unfortunately, as I guess both of you know pretty well, with these NV experiments, you're averaging, 100,000 to 1,000,000 times to get each of these data points. So we actually don't really have a good sense of what the ionization dynamics look like because you're really averaging over all of these configurations. That being said, it does seem like there should be some path towards looking at like correlations to try to get at some of these timescales. And we have not tried going back and doing some of that more detailed characterization.
Okay, and then maybe one last question. So Bill Phillips asks, toward the beginning of the surface spin section, you showed free induction decay on which appeared to be superposed a fast oscillation on which you did not comment. What is it? I think that was the sort of coherent, yeah, I think.
Oh, this. Yeah, so this is what you would see if you saw coherent coupling to one of these surface spins. So you should be able to see kind of reversible excitation basically between your NV center and the surface spin. And we do see this, in a couple % of NV centers, but not as often as we would expect.
And so do you have a picture for what the difference is between a defect that allows you to still see that coherence, or maybe that shows you this blinking, and then the ones that seem to be moving around all the time?
I have a guess. So the guess is that you just have some other kind of surface defect that's deeper than everything else, right? So it just ionizes very weakly under our excitation conditions, but we don't have evidence for, one thing or the other.
Okay, great. I think we can move on to the last section of your talk.
This is going to play this movie. Okay, so with the last, I guess, 10 minutes or so, I thought I'd tell you a completely different story in a totally different material system. So, hopefully what I've been able to convince you of is that we can take direct materials characterization and spectroscopy, correlate that with quantum measurements, and try to use that for systematic improvements and understanding the system better. So the sort of next thing that, we started looking at in terms of deploying this playbook was the superconducting qubit. The transmon is basically a Josephson junction connected to a capacitor and a resonator. And this has formed the basis of some really incredible demonstrations in quantum information processing in academic labs and also in two or three of the big industry efforts. So this has been obviously an enormously successful platform. And there was a lot of steady improvement in the coherence time of planar transmons for a long time. So from the late 90s up until about 2012, there was sort of this steady march of improving these systems. But one thing that people don't mention as much is that the last time somebody set a record for a planar device was about 2012. So all of the improvements since then have been things like 3D cavities that can have much longer lifetimes, but the qubit coherence times are kind of stuck at around 100 microseconds, despite enormous effort around the world. Okay, so we went into this and thought, well, maybe someone needs to just take a direct look at the materials and see if there are any obvious improvements that you can make. And we sort of immediately had two hypotheses for the dielectric loss. We got together with, this is all work that's done in collaboration with Andrew Houck's group, and we got together with Bob Kava, who is a solid state chemist in the chemistry department here. And we took a look at what qubits are people making now and what could be the problems. So our two main hypotheses were, one, that you can have a lot of contaminants on the substrate and on your device that just lead to dielectric loss. And to give you kind of a sense of the scale here, if you have a loss tangent of something like 10 to the minus 3, which is a pretty typical loss tangent of stuff in general, and you put that on top of a qubit that has a surface participation ratio of something like 10 to the minus 4, which is a pretty standard number, then that limits you to a Q of around 10 million, which is very close to the limits that people see right now. So this 100 microseconds is the Q of around 1 million. So it doesn't take very much to basically, give you exactly the losses that people see. The second issue, or the second hypothesis, is that IBM and Andrew Houck's group use niobium as the capacitors, I guess that's in this diagram here, as the capacitors and resonators that are connected to their aluminum oxide Josephson junction. And Bob sort of pointed out that niobium oxides are incredibly complicated. You can basically have many different stoichiometries. All of these phases are metallic and, kind of poor metals. So this can just lead to straightforward resistive loss that really kills your lifetime. Okay, so we set out to tackle these two issues. So the first is that it turns out that if you just take an as-received Sapphire wafer, which is what they are generally fabricating on, they look absolutely terrible. So if you just do kind of standard AFM or X-ray photoelectron spectroscopy, these are really horrible looking, really much, much worse than any diamonds that we've ever looked at. So what we did was we set out to come up with a way to do Sapphire substrate preparation. So we can do some cleaning, we can do a little bit of gentle etching of the substrate, and we can even do high temperature annealing to really recover these kind of atomic terraces. And what we found is that, you get these heteroatom contaminants from various types of processing that happened to this wafer before we got it, and we're able to get these very pristine surfaces by the end. The second piece, and this was really Bob Kava's suggestion, was, he said, why are you working with niobium at all? Tantalum has a perfectly fine superconducting critical temperature, and it has much, much nicer oxides. So what we were able to do was just replace niobium with tantalum metal. It turns out that you can actually get really nice oriented growth of the correct phase of tantalum on Sapphire. So kind of the tricky thing about tantalum is that if you just naively grow a thin film, you get a much lower TC superconductor, you get the beta phase. But what you can do is just heat up the substrate and you get BCC tantalum, which is the alpha phase. And then what we see in these films is basically a 2 nanometer thick oxide everywhere we look that does not care what you do to it. You can throw it in acid, you can throw it in base, you can heat it up, and you sort of always have this 2 nanometer thick oxide. And it's very robust and stoichiometric. So you always see Ta205. So in contrast to niobium, where you just look at it funny and it turns into a new stoichiometry. And just to give you a direct comparison of these oxides, this is data that was taken by Conan Weiland and Ignace Yarrigue at NSLS2 at Brookhaven. So they had this nice data set on niobium that they did in collaboration with Andrew's group, where you can see that you get all of these different suboxides, and you get a lot of effective oxygen diffusion into the metal. So it's really this very messy layer. Whereas in tantalum, you have this basically atomically sharp interface to within the resolution of their technique, and very little suboxide contribution. Okay, and then finally, after sort of improving just the substrate quality and changing the metal, we then had to worry a lot about what our fabrication was actually doing in terms of getting a good edge morphology. Because if you get anything that's kind of sharp or weird looking, it's sort of well known in the field that because you get this field concentration in these nanoscale metal structures, then that can really enhance your surface participation ratio, which enhances your losses. So we did a lot of fabrication development to be able to get these smooth structures. Okay, so the headline result after all of those improvements is that we're able to now make planar transmons with lifetimes exceeding 300 microseconds, which is a factor of 3 or so improvement over the prior state of the art, across many gigantic efforts. So this is all that you need to know. You don't need to listen to the rest of it, but basically we're now able to get these really long T1s. Just to show you that we're not cheating, we can also, look at T2, and we find that we have a T2 that's up to around half a millisecond if we do dynamical decoupling. And we can look at the time variation of these parameters. So this might come to a surprise. This might come as a surprise to anyone who works on atoms or even NV centers, but it turns out that transmons generally show a lot of variation on hour to day long timescales in their T1s and T2s, which is a really intriguing problem that I'd kind of like to tackle separately. But anyway, what we can do is to provide an honest comparison, look at kind of the time averaged values of all of these things. And we find that we really do have this robust improvement. Okay, so just to just sort of summarize this very short story, we found a really big leap in performance for superconducting qubits with some very simple material changes. And I'll just point out that there are many more to explore. So I think the lesson here is, we tried one more superconductor and we're able to beat this bound by about a factor of 3. You can just write down the list of, all of the superconductors with reasonable TC that are depositable and fabricatable, and that list is totally tractable. So I think we're probably just going to do that. But with tantalum, which is very exciting, we're now trying to systematically study how different material properties affect relaxation and coherence and try to get this next factor of 2. The real prize here is that if we can get to a T1 of about a millisecond, then you could do things like break-even quantum error correction, which would be really exciting. So just as a first kind of taste of some of the systematics, what we've started doing recently is try to speed up these measurements by doing very systematic studies of just quarter wave resonators made out of tantalum. So the idea is that, you eliminate any variation in your junction fab, which allows you to do much more systematic study. Tantalum is pretty robust to processing, so you don't have to worry about the kind of fragility of aluminum. And now because we're working, because we sort of get away from aluminum, we can operate over a much larger temperature and power range to try to uncover microscopic mechanisms. And importantly, these measurements can just be much, much faster. So here's an example of one of these data sets. What we see is that the quality factor for these resonators really changes dramatically with power. This is sort of characteristic behavior of losses that are dominated by 2-level systems because you can saturate the 2-level systems. Okay, just totally full disclosure, I was completely expecting to enter this field and find that 2-level systems explained nothing about the behavior of superconducting qubits just because it seemed too easy. But it turns out that it explains almost everything about the behavior of our resonators. So if we do a full power and temperature dependence of one of these resonators, then what we can see is that at very high temperatures, all of these curves kind of collapse onto each other because you just have equilibrium quasi-particles from the gap, the superconducting gap of tantalum. And then you have this kind of nice gentle slope here that actually comes from equilibrium population of 2-level systems. And then this initial drop here with temperature actually comes from the saturation parameter of 2-level systems changing as their T1 and T2 change with temperature. So we think that everything here is pretty nicely explainable by having 2-level systems that are associated with the surface. And then just to probe that a little bit in more systematically and in more detail, what we can do is take this kind of nice plot that Chen Wang put together in Rob Shulkoff's group of many different qubits with different surface participation ratios and their quality factor, and then kind of plot our data on top of it. So these blue points here are all of our tantalum qubits, and then these little blue crosses are these resonators. So we're now trying to sweep the surface participation ratio. And we indeed do find that we're on a scaling that's around a factor of 5 better than what was previously reported in the literature. So that's very exciting. And what we're doing is using this now as a basis for further improvements. Okay, so with that, I'll just acknowledge all of the students and postdocs and collaborators who are involved in the work. So the NV work was led by P. Sangtoesen and Leela Rogers and Bo Dwyer. And in the surface spin story in particular, we were really collaborating heavily with Misha Lukin's group for this giant data set, and that was led by Bo Dwyer, Alana Urbach, and Dolev Bluvstein. The superconducting qubits work, this initial sort of tantalum work was led by Alex Place and Andrew Hauk's group and Leela Rogers in my group. And this more recent resonator work has been led by Avik Dutta, who's a new postdoc in my group. And actually this really incredible group of undergraduates, Trisha Madhavan, Huang Li, and Yuchi Gang. Trisha is currently searching for grad schools. So she's doing all of her visit day stuff. So I encourage you to aggressively recruit. And Huang and Yuchi are going to come around the bend in a couple of years. And then I have a very large number of collaborators and funding sources to thank. So I'll just stop there and take your questions.
All right, well, thanks a lot, Natalie, for a really fantastic talk. So there are some questions. So first of all, direct everyone to the Q&A in the webinar if you're there for a tantalizing pun by Bill Phillips. But in addition, we have some questions. So Francisco Machado asked, can you comment on what people think might be the possible origins of the slow variations of T1 and T2 in the transmons that you showed?
Yeah, I feel like this is the kind of topic where I'm going to get in trouble with this community. So to me, if you really have something, so let me just tell you what our empirical observations are before I start speculating. So what we'll see oftentimes is like, you'll have a pretty stable T1, and then all of a sudden something will happen, and then your T1 will change, and it'll stick there for like a couple of hours, and then it'll change again. And then sometimes you'll see that it fluctuates rapidly and then suddenly settles to a new value. So to me, this really feels like cosmic rays, because it's, I can't think of anything else that gives you these extremely rare events on a time scale of hours or days. That doesn't tell you the whole part of the story, because then it's like, what are the cosmic rays doing exactly? So presumably they're making things like non-equilibrium quasi-particles that then just have to like find some happy home somewhere. But then the actual metal itself is a very tiny cross-section for these cosmic rays. So whether or not this quantitatively makes sense is not clear. I'll also say there is a really intriguing paper on the archive the other day. I'm trying to remember if I can actually like summarize this properly, but they basically saw that their devices took many days to settle after cooling down. So there's some kind of extremely long thermalization timescale that they don't fully understand. Yeah, I mean, those are kind of the two possibilities, I think. I'm sure that that's not an exhaustive list.
Great. So let's see. We had a question from Aziza. Is the Q limit from loss tangent on top of the superconductor frequency dependent? Does it get worse or better depending on the frequency of the device?
No, from what we've been able to see, at least over the narrow range that we look, which is typically between 5 and 7 gigahertz, we don't really see a Q dependence, or a frequency dependence. When we do see a frequency dependence, it's usually something really annoying, like we've accidentally made a mode in our packaging, and then you're just seeing coupling to that mode, but it's easily avoidable.
Okay, and then maybe we'll bookend the Q&A with another final question from Bill Phillips. So are there any insights into what the two-level systems actually are?
Yeah, that's no is the very short answer. So of course, this entire field of studying two-level systems and their dynamics really started when Phil Anderson was looking at like the heat capacity of amorphous materials and trying to look at what happens in glasses when you have like tunneling of atoms that go to different positions. So I guess Rob has kind of a nice joke about it that because of that, people think that anything amorphous is like original sin because you're just going to get two-level systems in anything. The candidates are kind of straightforward. You can either have atoms that tunnel back and forth, or you can imagine having some, dipole associated with just, some particular impurity. It's basically anything that looks like a saturable. All that two-level system means is that you have a saturable absorber, which sort of describes, everything. The only thing that it rules out are these more classical dielectric loss mechanisms, like if you have some Raman process that, gives you some photon scattering or something.
Okay, great. Well, thanks a lot, Nathalie, again, for a really fantastic talk. And so now I'm going to hijack the screen sharing just to advertise the next round of talks for next week. So let's see here. So the Vamos next week at the same time, same place, will be Hannes Pichler from University of Innsbruck, who will be talking about from many body physics to quantum optimization with Rydberg atom arrays. And then the quantum science seminar, our sister seminar over in Europe, which takes place on Thursdays, will be Jeff Steinhauer from the Technion in Israel, analog cosmological particle creation in an ultra cold quantum fluid of light. So we look forward to seeing many of you or all of you next week. And in the meantime, I encourage everyone to move over to the other Zoom room where we'll have a nice informal discussion with Nathalie, where there'll be a chance to ask some of the questions you didn't have an opportunity to ask during the seminar, and also just ask her any other questions you have and chat with her. And I'll put that in the YouTube as well now. So thanks again, Nathalie, and we'll see you there.
Thank you.